Let's draw the mechanism and all the products here. As usual, I find it helpful to put in these asterisks, and again, these are not dots for radicals. I just like to put dots on these two key carbons in the dienophile. Oh, before I forget, I should just mention, remember that the Diels-Alder is only a reaction between alkene carbons. It's only a reaction between alkenes. Sometimes people think that maybe this can do the Diels-Alder, say a carbonyl, but it's only a carbon-carbon double bond that can participate here. So carbon-oxygen double bond is not going to be participating in the Diels-Alder. That's a mistake that people make. We know this can be an activating substituent. This carbonyl can be an activating substituent, but it's only the carbon-carbon double bond that actually has the electron pushing arrows. That's a mistake that sometimes people make. Now this is a little trickier than the problems we've done before, although it looks like you guys both know how to deal with this. Why is this trickier? Because we had a cyclic diene. We haven't dealt with any cyclic dienes before. There's really a different way to draw the product for a cyclic diene, but it looks like both of you already learned the basic idea for how to do that. Both of you look like you're already familiar with this idea. This is the general model for drawing the product from a cyclic diene. And here again, I find it really helpful to show where the asterisk carbons ended up, where the dotted carbons ended up. A lot of the time I forget to put the double bond on the back here, but we need this double bond. And by the way, what happened to this atom over here? Well, that got bent up. So the convention here is that the substituent on the diene gets bent up. I think sometimes it's called like a tent pole or something. So the substituent on the diene just gets bent up above the regular ring. Remember, what do we get? What's the basic product from a Diels-Alder? Cyclohexene. Well, here's the cyclohexene down here. Down here is going to be our basic product. And what are we going to do with this ring that we started with? We're going to bend it up here. So this atom over here is the same as this. Putting in some numbers might help here to see all the relationships. That's the basic way. So when do we need this approach? When we have a cyclic diene. We wouldn't need this for a cyclic dienophile, but we need this for a cyclic diene. Now we need to deal with this substituent over here. Use condensed notation. Now, it's really possible that the substituent can end up pointing down, or that it could end up pointing up. Either of those are fine. And I suppose to really emphasize that this is down, you could also put this on a dash. And to emphasize that this is up, you could put it on a wedge if you like.
Why would it end up doing both?
Pardon?
Why would it end up doing both? Because didn't we say it has to be like consistent with the
Right.
substituent is the outside?
Yeah, well, that's a good thing to think about. Now, here's the substituent on the diene. Is this inside or outside?
Inside, but they're not stereocenters, so you don't put dashed in one.
Well, now this is a stereocenter down here.
No, not that one. On the left, the inside and outside one
Right.
wouldn't be dashed or wedged anyway.
This is a stereocenter. This is a stereocenter. It is attached to 4 different things. Now, this is a little bit similar to chair cyclohexane in the sense that we don't always use wedges and dashes for these types of pictures. We just draw things up and down, or axial and equatorial, so to speak, and we hope to use that to indicate the geometry. Well, let's spell this out a little bit more. Now, so we have to draw an endo and an exo product, say. So is this the endo or the exo product?
Oh, okay, that's the endo.
Because here, this substituent ended up pointing opposite to this substituent. Maybe I'll go ahead and number this.
I forgot that there could be both. It's not like before where we were thinking.
Right.
it was just-
Remember that just because I wrote it like this doesn't mean I only wanted the exo. Remember, they don't usually actually use the drawings of the reagents to tell you whether it's endo or exo. They would use words. So in this case, this number 1 substituent ended up pointing up, and this ended up pointing in the opposite direction, which is down. Well, that would happen if they had if we had an endo attack, because then they would have started in opposite directions. This is kind of pointing away. Did I erase that?
And wouldn't the endo product be more favored?
Right, so here these are pointing in different directions. So that would occur for when this is endo. So this would be the exo attack. In this case, if this is pointing in away from the back and this is pointing away from the back, they would be similar, so they should still be similar here. And again, you can really emphasize that. Sometimes people put in a dash here or a wedge here to emphasize that this is down and this is up. You might see it either way. Now you were bringing up another issue. Suppose they told you to draw the endo product, well, you would draw this. Suppose they told you to draw the exo product, you would draw this. If they ask you for all products, you would draw both. But what if they ask you to predict which is probably the major product? Well, you're remembering correctly, endo is usually the major product. So we can memorize that endo is usually the major product. It's true that the endo attack is usually the major product. However, if they said all possible products, you should definitely draw both of these, because you definitely can get both.
Why is that one the endo?
This one over here?
Doesn't the endo point closer to?
But in relation to the inside?
So here's what an endo approach would look like. The endo approach would be if this substituent was pointing towards the back of the diene. But if this substituent was pointing to the left, this substituent is pointing to the right. So they're kind of pointing, so they kind of started in opposite positions to each other. If this started in the endo position, it would kind of be opposite to this inside substituent here. So they should end up opposite. Do you see how this is pretty much pointing up? This carbon over here, this is pretty much pointing up. Maybe another way to put it is, remember there is another substituent on this star. There is another substituent. What else is on this star?
H.
Yeah, there's a hydrogen. Those could be drawn like this. Now the key point here is clearly this is in the up position and this is in the down position. Relative to here, these are both pointing down relative to this that's pointing up. So here, up and down are probably more useful terms than wedges and dash. When we use this type of picture, thinking in terms of up and down is the most useful way to think about the stereochemistry. By the way, that's important. We should recognize that there are other positions on these stars over here. There's an up position and there's a down position. So here's the up position, here's the down position. If there had been an actual substituent here, like an alkyl group, we would actually have to draw it in over here. So does it make sense now why this would be the endo product?
Yeah.
Okay. Okay, so now we've learned what to do when the diene is cyclic. I guess we still have some issues here. What are our issues? The issues are, what if we drew these two cases as if this was, as if the substituent was pointed down in both approaches, but it could just as well have been pointing up. And that would give us then it would end up on this carbon, which is a different picture. If the substituent is here, that's not the same molecule as if the picture is here. And this could again be either up or down for endo or exo. So it's plus.